there is an Emacs mode. I think it's the case that company coq actually has a nice feature that's like tooltip, and you can put the cursor over, is it company coq? There is some tool that allows you to put the cursor over a tactic, and it will show you the proof state that was associated with that. That was the proof state that tactic was applied to, which isn't quite as good as, officially sort of codifying precisely where that came in the proof term, but is slightly helpful. Yeah.
When you have manual proofs, it's kind of easy to explain to somebody what's going on. Right? What kind of comment would you add to this one-liner? If you were to show this one-liner to a colleague, and, without any context, you'd probably put what comment to explain what's going on. Mm-hmm. What would you write down? Well,
I think the right way to engineer these tactics is you have like these intermediate tactics we define that are solving a lot of these goals, like find EQN and find rewrite inf. And a key part is, much as like any other software engineering task, it's good to have a tactic that does one thing and does it well, and you can comment and define what that tactic is doing. And you could explain this proof script by saying, you look up what the comment is that describes what this tactic does, and says, we try and do this tactic, and we try and do this tactic, and it sort of follows from that description.
For example, if you're just as we have code and then an algorithm is a high-level description, would you say, oh, we proved this theorem by making a bunch of introductions, we get rid of some cases using inversion, we find some equations and we try to rewrite with them, and that's it. Right? The details are automated. That's essentially how the proof works. Is that how you would explain it to us, and then we could try to write it like this?
Yeah, I think that's probably safe to say. I mean, actually, yeah, there are many different ways to structure your proof, and I don't think there's a strict agreement on what's the right way to construct your proof script in a way that it's easily understandable, or indeed, there is an agreement on whether or not it's necessary for your proof scripts to be completely understandable to someone who's not deeply versed with your tactics. So, I don't know. That's my answer. I don't know. You should strive and, just try and approach this with the same good engineering, the same good engineering, software engineering techniques that you have when you're writing programs. And indeed, if a proof is particularly complicated or involves some particular insight, you should probably explain that insight in a comment around the proof, right? Because that's more informative. The point, that explaining the intuition in a comment is much more informative than looking at a proof script in general. Like any sort of English description is probably going to be better. Leonard?
And another technique is that if there are some cases that are a bit more interesting, you isolate them as additional lemmas, and then you can call them either explicitly or as part of such try or hint database.
Yeah.
They at least have their own names, so that you can structure your explanations.
Yeah, I think that's actually a very good. I'll repeat that for posterity. If there is a particularly interesting bit of reasoning that's required, it's useful to separate that into a sublemma that you can explain exactly what the insight is associated with that lemma, and then its use in this high-level proof can either be incorporated using auto or apply or something, and then it's a little bit easier to, this is just good engineering practice. Shucks, we got 5 minutes left. I really wanted to cover eApply and eAuto really fast, unless the question is super burning. Yes.
So maybe to meet halfway there, is there a way that when you open a bullet, say a bullet for one of the cases of the induction, can you say which case you're opening? And in that way, it's sort of not have it be comment. It would be checked, because then you say which case you're in. Is there a syntax for that?
The question was, is there some way of attaching some piece of syntax to a bullet that identifies and is checked by the proof assistant that bullet, what case that corresponds to, and have the way the proof checker ensure that is an accurate representation of the case that generated that bullet? The answer is no, but that's an interesting feature, and you should think about how to do it and submit a pull request.
The early version of Software Foundations about 8 years ago had something that was a little bit.
Yeah, but it didn't do any checking, right? It had this case thing, but it didn't.
Remember how they realized?
Yeah.
But you could do it with like a biological contact tactic, right?
Yep. So I'd really like to do e-apply and e-auto really fast, just because these are really useful, and you will want to use them eventually. So, shucks. So, okay. So here's this example we just saw in the last lecture, where there was a sequence, and we were trying to show that this program reduced to, starting in this state, reduced to this state. And part of the sequence constructor requires you to supply the intermediate state, right? So here we look at this, and when we apply this constructor, we have to explicitly spell out what argument this gets applied to. What this argument corresponds to the intermediate state, and we supplied it with this with context, right? This with syntax. So, right, that's what this says down here. But if we left out the with, when we tried to apply that constructor, coq would say blah. I can't find an instance for this variable, and it wouldn't proceed. But this is really silly because we can figure out what this the intermediate state has to be immediately from the subgoal that got generated, right? It's sort of backwards that we have to do that. And e-apply allows us to eliminate the silliness, right? So, so it's easiest just to see what this looks like in action here. So here's that same goal. If we try to apply eseek, it fails for the exact reason it can't find an instance for that variable. Now when we say e-apply, what does it do? It succeeds, and in the goals that get generated, we have these weird little question mark st prime and question mark st prime, and these are meta variables. And what's going to happen is we're going to resolve these meta variables. We're going to fill them in as part of the proving these goals, right? So in a particular, we know what st has to be from this eassign thing, right? The rule dictates what the final state is going to be after we run this command. So we apply that, and what goes on under the hood is like coq takes that hole and fills it in with what the value that it needs to be through unification. And indeed, this just works. So real quick, here's a slightly different example using transitivity of less than or equal to. So here, there's an e-transitivity tactic, and it's going to give us these same holes, right? E-transitivity says if m is less than n and m is less than, say, O, then m is less than O. In order to apply that normally, we need to say what this intermediate number is, but when we use e-apply, we leave it with a hole. And if we actually show the proof at this step, it's a little bit hard to read, but let me pull this up here. Oh, this is actually, that's a little bit hard to read too. Let's look at this. So e exists does something similar. So if you actually look at the proof term that's getting generated here, in just the same way when we apply a lemma, you can put a little underscore and coq will infer what that has to be. Basically what's happening with these little question marks is in the proof term under the hood, these are underscores, and you're making a promise to coq that when I complete this part of the term, you will be able to infer what that argument had to be from this argument, right? So in particular, when we say reflexivity here, reflexivity says I can solve a goal of the form x equals x. So here it says I can solve a goal of the form 2 equals 2. I know the right-hand side is 2. I can solve this if n equals 2. I can infer it, and so it does. And so it unifies n with 2, and it solves the goal. And if I print e exists, or x1, I guess, you'll see the proof term that I get down here. Now this hole has been filled in. It inferred what this had to be based on this argument. And that's it. And it turns out there are several tactics that have variants like this. There's e exists, there's e constructor, there's e auto, and they all have a similar style where if it tries to apply something, if there are some unapplied arguments, it puts them in with little holes that get resolved during the rest of the proof. And it turns out that this is, this is very useful for automation. It's sort of like a promise. I'm going to tell you what this is as part of proving these subgoals. and it's great. And there's just one note here. One might think that the e-apply and e-auto are more powerful than e-apply and auto because they apply to strictly more cases. You should use them all the time. Of course, the issue is that they're significantly slower, as it notes here, especially e-auto, because e-auto is much less constrained about the things it can apply to any given goal. So it's going to try a lot more things and generate a lot more of these little variables which involve some overhead inside the proof assistant. So the experts tend to use apply and auto instead of their E variants most of the time, unless they're not doing the job, unless there's a specific reason to use them. And that is all I'll say about these E variants. You should try and use them when if you run into a goal where you try and use auto and apply and they fail, you should step back and try and use e-auto and e-apply instead and see what happens. Okay. And with that, I've run over already. So unless there are any burning questions, well, if there are any burning questions, you can come talk to me. Otherwise, have a good lunch.